Right, in this little video, I'll try and explain some things about system identification. And one of the things that we'll have some data, use data from the rig to identify transfer functions. And so typically we might have, say, this might be the elevator movement in the plane, in the tunnel, and this could be the change in, say, pitch angle. So we have some data now, and from this data we're going to try and extract a transfer function. Now there are two ways of doing this. One is you can assume a transfer function structure. That means a structure of the GSB, don't know the parameters, or you could just assume the number of poles and zeros and use a Matlab package, system identification package, to work out the parameters. So there's two ways of doing this, probably more, but these are the two ways that I'm looking at. So if we have a look at this first method, what we do is the input signal here is the elevator movement, and the output signal here is the actual pitch angle of the aircraft. So we've got these two signals and they're applied to this block diagram here. So this is the output of the real system, and it goes straight down to a scope. This is the input to the real system, and then it goes through a transfer function here and comes out. Now if this transfer function is exactly the right match with the real system, the output here will be identical to the output from the real system. So you'll have a model's output and a real output. So if we'd applied this signal to the model, and the model had done this exactly the same as the real one, then we'd say the model must be perfect. Now there's different models you can have here, but this one is a first order system and a second order system and a gain. So this is a model that you should understand, because we've done first order systems, done second order systems, and the gain just shifts up and down the graph. So I'm going to explain now how you could use, if you didn't know what the numbers to put in here, how to adjust these numbers now so as to get the two outputs, that's the output from the real system and from the model, looking as close as you can to each other. And the thinking being that if the two outputs are the same, then the model is quite good. So let's have a look. This could be this could be the real output here, and this could be, say, the model output here. So the model output at the moment is quite a bit different from the real input, and this is the current transfer function we've got. So we've got to find some way now, changing all these numbers to make the blue and the red line match up. So the best way to do it is to use this number here first to shift the blue line up, so as the blue line ends up roughly the same point here. So we'll need to shift the red line upwards by making that number bigger. So make that number a bit bigger, we can shift this up. That's the first thing to go for, is get the steady state of both matched up. So we could, and when we've done the final of messing with all the parameters, we've got all these numbers right, we would hope to get something that looked a bit like it's not going to be a perfect fit, but it's not going to be far off. This would be a good one. This is how you'd know it had worked. Now to explain some of this, there's a little example here of a second order system, and you can see that the parameters from these two are not the same. So we're going to find a technique now of massaging say these parameters here until they become equal to those there. So as I said before, the first thing you do is you look at the steady state gain. So if your system is a bit high, you move it down. If it's a bit low, you move it up. So one will be your real system and one will be your model. So the only thing you can do is move the model. So if this was the model here and this was the data, it's coming out a bit low, you could move it up by increasing k. So if we increase k, what will happen is we'll then get the two signals matching up here. So that's the first thing to get the steady state. Then you can look at the frequency now. So this is the frequency of the model, and this is the frequency of the real thing. So you can see the frequency is too high because it's a higher frequency than the blue one. So we need to lower the frequency. Now the model, this parameter here is the natural, this is it's s squared plus 2 zeta omega n plus omega n squared. So this term here is omega n squared, and so if we change that number, we can change the natural frequency of the system. So coming back to here, if we need to lower the natural frequency, we'd make omega n smaller. If we need to make it faster, we'd make omega n bigger. Now, one thing to bear in mind is the omega n squared appears there and there. So if you change that 9, you'd have to change that as well, because it's just a sort of trick that you've got to do in the model. The model's like omega n squared of s squared plus 2 zeta omega ns plus omega n squared. This has got a gain of 2 unfortunately, so it's like 2 omega n squared there. But so if you change that number, you need to change this one as well. Otherwise, if you don't change both, the steady state gain will change. Then you'll have to readjust the steady state again. So we can change then the frequency. So we can then get the frequencies roughly right. So once you've got the frequencies roughly right by getting the natural frequency about right, we can then look at the damping ratio. That's the overshoot and undershoot. So we need to, there's too much overshoot here. So that the middle parameter here is the one that controls the damping ratio. So if we make that number bigger, you'll put more damping in. Make that number smaller, you'll get less damping in. And so then you can, in this case, you need more damping, so you have to make the number bigger. So we'd have to make that number bigger, and then that would pull that overshoot and undershoot down. And when you've done that, then you can pull it down, and as you pulled it down more and more, you could then get it to fit one on top of the other. There's a perfect fit. And so that's how you can use then this type of model here, which is one we might use in the project. If I can find it. We might use a model of this form, which is a first order lag and a second order lag. The first order lag just affects the start of the transient response. So if your start transient response is a bit fast, you could make these numbers smaller. If the start of the transient response is a bit slow, you can make those numbers bigger. But you can have a practice with this, and we'll do an example in a minute of doing this. But there's a method for adjusting these parameters so as you can get a good fit between the model and the real system. And then the alternative approach is to use the system identification toolbox. So to run this, you just type in system with a capital I there, identification in Matlab prompt, and this little thing comes up. And then you can use this then to actually generate transfer functions as well. It's a little package. It's fairly easy to use once you know how. And again, in the video, I'll also demonstrate how to use this to work out a transfer function. And what we'll get is we'll get data off the rig, and then we have to read that into the program. There's a program for doing that, which like loads in data and then manipulates it. How that program works, we can discuss at another point. Right, so here's a real example now. So we've got a transfer function 10 rest was 10, 5 s squared plus 4 plus 5 and a 1 in here, and we're trying to get the right numbers in these transfer function boxes by comparing. This is the real output coming down here onto the scope. This is the input going into the model and coming out as a model output, and we can compare the two here. So if we run the program now, we can look at the two. So you can see now they're significantly different, and the yellow one is quite a bit lower down than the blue one. The blue one's the real one, the yellow one's the model. So we need to push the model up. So to push it up, we can say change that number, double it, say 2. Run it again. Then they're looking more similar in the steady state here. Now, next thing is you can see the frequency of the yellow signal is a bit lower than the actual signal. This signal here is slower frequency than this one because this peak is ahead of this one. So this is a higher frequency than that one. So it means the frequency needs to become a bit higher frequency. This is a low frequency. This is a higher frequency. So we need to increase the frequency. So we do that by changing this number here. So click on that box. I know what the answers are, but if you change it to 9 and this one to 9, then what we'll see this time is get a closer match on the frequencies. So now that's not worked, has it? Let me have a look at this. Probably the frequencies are the same. I'm just going to check the frequencies. You can measure it from peak to peak. So I'm going to do a peak to peak on this, which is that much. On this one, the peak to peak. Yeah, so if you look at the peak to peak on these, that's the time from there to there. It's the same as the time from there to there. So the frequencies are in fact the same. They don't look the same, but they are. But what's happening is the reason for that is this yellow one's coming up a bit too fast. So that's what's speeding it up and making it look like it's not the same frequency. So we need to slow this down now. So if we slow that down, let's slow it down to say 6. Again, you have to make these two numbers the same. So if you have a 6 in there, you got 6 in there. Otherwise it'll affect your DC gain. Run it again. And this time, well, it slowed it down a bit, but not much. Let's try and go down to, let's go to 3, shall we? Run that. So this time, it's not too bad, but this time it seems a little bit, still not matching very well. It's matching along here, not too bad, but the yellow one's still a bit. This could be due to the damping ratio. The damping ratio on this one is down. Don't know why I didn't do that one next. Better to get, when you're closing in on these, if we go back to this, we can pull this signal down a bit by increasing the damping ratio. So probably better off going for that number first. Lost my order of doing things here. So we made that a 3, for instance. Then run it again. This is increasing the damping. So that's then brought these two signals more in line. Now it's easier now to adjust the yellow one. So I got the order wrong. Should have done DC gain first, frequency second, damping ratio third, and then go for the parameter last, the 10 or respers 10 or whatever it was. So this is, you can see this is too slow now. The real one's a bit faster. So if we speed it up, so we make it a 5. Run it again. Then this time, it's not bad, but it's a little bit faster this time. So 5's a little bit fast. So tried 3, tried 5. So I go for 4. Run that one. And you get more or less the perfect match. So now we've managed, with the perfect match, we can say now that these are the parameters which now represent a reasonable model for this given system. So you change that one first, then the frequency, then the damping ratio, and then the time constant of the pole, this is like a little actuator that moves the elevator, and this is like the flight dynamics of the plane, which has been modelled by like a little second order system, and that's a gain on the system. So go for that one first, then those two numbers, then that one, and then those. But keep those the same. Keep those the same, as you otherwise you'll change the DC gain, and then you have to change this number as well. It saves you changing all the parameters are orthogonal to each other. So if you play with one of those numbers, it doesn't affect any others. So that's one way now of carrying out system identification. And the other technique now would be to use the system identification toolbox. So we could do the same sort of thing now with the system identification toolbox. So I'll explain that next. Right, so second method now is using the system identification toolbox. Now, in order to do this, you have to have some data. So you'll have run the rig and stored the data onto a file. Now I've stored mine onto something called test9.mat. So if I run this program, it will then load in the data and plot the input, which is the elevator, and plot the output, which is the change in pitch angle. Let's have a look at that first. So this is it now. So this is the change in pitch angle of about 5 degrees. There's a 5-degree pitch change in the aircraft, and this is the elevator motion here that did it. Now, in order to get a linearized model, we have to move the 20 down to 0. So we've got to pull this signal down by subtracting 20 from it, and this is called an offset. So when you run the thing for the first time, you can look at the data, you can work out what this offset is, and then you can put that number then into the program. So in this case, I'd put the offset as 20 just to show you, but we could then put the offset as 0. We could put the offset as 0, and then hopefully this time it will come out, it all starts as 0. So now we've got the signal. This is the output signal going to 5 degrees, and this is the input signal. The input signal starts off a little bit earlier than the output, so you can tell which is which. And this is the elevator, and that's the output. So this is the data now that we're going to use to identify the transfer function. So if we, to get this to work now, we type in system identification. Now, unfortunately, this isn't on the screen. I can maybe I can't move the screen about. There is a system identification with a capital I in front of identification, and press enter, and then the package starts. So I'm just going to try and move the package down here. So we now need to import data. Now in the program that we had, it called the variables y and u, just to make life simple. So we say time domain, and we give the input now. So the input is u and the output is y, and the sample time was 0.05. With the sample time you'll be able to compute, and it's fairly constant once you've got your configuration running. I can't remember what it is, but it's probably going to be somewhere in the region of 0.05, but we can get this number from the rig as we run. So we've set this up now, and we click on import, and that then imports data into the package, and then we go to estimate, this box here, estimate, and we go for transfer function models, and it now asks us now how many poles and zeros we want. So in our particular case, we're going for 3 poles and no zeros, because we know this is the answer to our problem. Now this you don't know always, so you might have to try different combinations of numbers here and see which one works best. But this allows you to choose the number of poles, that's things on the bottom, and the number of zeros, that's things on the top. And you can then go for continuous time and click on estimate. Now, if we then close, this has then given us some data here. So we click on that one now. It now gives us the transfer function that it's worked out. Now, if we do export on this, it then transfers to the Matlab workspace. So it's now in the Matlab workspace. So if we type in TF1 here, this is it'll print out the transfer function here, but we don't want it in this particular format. So if we type in ZPK, which gives it in pole 0, ZPK TF1, then here's a transfer function. And this now, notice, is what we had. It's the 4, the 9, and the 2. 4936, 236 is 72. S plus 4, S squared plus 3S plus 9. So it's actually worked out now, the transfer function for us, which is the one that we had in the original system here. So it's worked this thing out for us using the system identification toolbox. Now, this doesn't always work perfectly. Down here, I've got a method for adding in noise to the system. Now, if we add in noise and rerun, this is the data I gave you before was like very clean data with no noise in. But the data you'll get off the rig will have noise on. So this is like a little noise generator, and it'll just show you for a given system how adding noise into it makes the thing not work quite as well. So if we run this for the moment, run that, we can just have a look at the output here. So this time you can see the input is fairly smooth, but the output now has got a bit of noise on. So it's got a bit of extra signal noise on. This is what you get in real signals. And this will mean that the system identification will still work well, but it won't be spot on. So depending on your run and the amount of noise you've got, you'll always get different answers. You'll never get the same answer because it's all corrupted a bit by noise. So we can see now how much noise can affect the system identification. Right, so just before we do this, we type in plot t comma y, which will plot the output. You can see now this has got this bit of noise on. So we've got now this noisy signal, which we're now going to feed into the system identification. So we type in here now system identification. And the package starts. We can then do time domain data, put in here U, and there Y, sample time 0.05, import. There we go. So it's come in here. So if we click on that one now, and go to transfer function models, 30, estimate, close, and go to here. Now it says generate this new transfer function here, which can be called TF2. So come out exactly the same as before. So I can not use the right data. Let's have a look. I've got that one. Transfer function model, estimate, close, click on this one, still giving me the same model. Oh, that's a nuisance, isn't it? Okay, just that hadn't loaded. What I did is I closed down the package, reloaded it. So here's the data here, which I've loaded in, which is the U and the Y, and this is my transfer function 2 now, which I'm going to have a look at. So I click on that one and we're doing the identification. You can see now this should have been 75 and that should have been 36 in there. Or if we get TF2 into the, so this is not identical to what we had before now because it's got a bit of noise in. So if we go into here I've made a mistake now. We need to click on that one and do export, and then write that one into the workspace. And then if we type in here zpk tf2, you can now see the 9 isn't perfectly 9, the 3 is not perfectly 3, the 4 is not the perfect 4, and this number is not exactly 75, but they're not far off. You can see they're within spitting distance of the correct values. So the effective noise, and the more noise you get, the more these parameters will go off the real ones. But that hopefully now will show you. You can have a go at running. I'll send you these programs as well. You can have a go at running these programs and just getting an idea how to use the system identification and the toolbox. So as when you get real data off the rig, you can apply these techniques. Obviously, one of the things, I did go through this quite quickly, you can try different numbers of poles and zeros in here. So if you over parameterize, let's just do an over parameterization. If we do estimate transfer function model, say we went for 4 poles and 1 0, so we've overcooked it now. If we do an estimate, it's done that for us. So this is the thing here, and this is it. So if we now move this one into the work domain, I export, and this is called TF3. So if I now do a ZPK TF3, and you can see now that what's happened is it's added a pole. These numbers are more or less the same as was before, but it's now added a pole and a 0 which almost cancel. So if you get pole 0 cancellation, this is indicating you've over parameterized your model. Now once you've got a model here, you still need to check out it's okay. So the only way that you can really do that is to go back to one of these programs here now and put the numbers here inside, put the model in here that you've got, and then compare it to the real output. This isn't the program to do that though. I've closed it down, unfortunately. It's the previous program, if I can find it. Open. No, that's the wrong open. Recent files. It's playing up. Here we go. Try that one, shall we? No, wrong recent file. It's useless Matlab, isn't it? This one. So what we do now is we'd put our model in here, and then these bits of data now would feed in from Matlab Workspace. This would be the input, this would be the real output, and then you could compare the two things here to see how good they were by putting your model in there. So you'd have to build that up as a Simulink block with the various parameters you got from your system identification, put them in there, then run this, and if it was a good fit, then they'd sit on top of each other. If it wasn't a good fit, they wouldn't. So that hopefully gives you a few little clues now as to what you can do with this package. I'll send you the programs and you can watch the video. So good luck with that.